Okay, now we've started recording. We're partway into our practice quiz. And, alright, so on the accumulated area function, what's true about the first one is if x is, let's say, I can put the equal to with either one. If x is less than or equal to 2, then we're in the left half, which is just the line that's going downhill from left to right. If x is greater than 2, then we're in the right half, which is the line going uphill from left to right. Okay, and the function, this one here on the right half is the easier one. The absolute value, you see, as long as t is bigger than 2, t minus 2, when you take the absolute value of it, the absolute value won't do anything. Like if t is 3, 3 minus 2 is 1, the absolute value of 1 is 1, the absolute value isn't doing anything. Plus 1, you get 2. So this function right here is just, the absolute value will disappear, and you'll get t minus 2 plus 1, which will be t minus 1. If the absolute value, if x is less than or equal to 2, so we're over on this half, then you see you get a line with slope -1 and whose y-intercept is 3. So it's negative t, negative 1t plus 3. So that's the function written as a piecewise function rather than as an absolute value function. It'll be easier for us to work with it like this. So now you are to find a of 2. Use your picture. You can use this function if you need to. And then find a of 6. And then we'll together work on finding a formula for a of x. So let me give you a couple minutes to get a of 2 and a of 6 on your own. And you can start on finding the formula for a of x. Okay, so I'm going to give one more minute and then I'll start. All right, for a of 2, the inefficient way to do it would be to get the area of this triangle and then the area of this rectangle. That's actually pretty quick though, but it's not as efficient as this way. You take the width times the average height. So how wide is this rectangle? 2. What's the average height? Well, when it's you can only use this if it's a straight line on the top, straight slanted line like that. And you have the two heights, height of 3 and then a height of 1. And you find the average by adding them together and dividing by 2. And so this turns out to be 4 divided by 2, which is 2. So 2 times 2 then is 4. Okay, and that's exactly the same thing we'd have found if we just counted the rectangles. There's 1, 2, 3, and then these two make 4. 4 little rectangles. All right, and then a of 6 is equal to, well, we're going to take this portion, which we already found, which was 4, plus, and then we're going to go out to 6, so we're going to do the same thing again. The width, from 2 to 6, the width is 4. And then the average height, there's a height of 1, and then there's a height of 5. Everybody following what I'm doing geometrically? And this average width and average height, any questions? Going okay with this? All right, so this becomes 6 divided by 2, which is 3. 3 times 4 is 12, plus another 4 is 16. So we found A2 and A6. Since this is kind of a complex problem, I want to make sure that everybody's okay with both of these. So let's just go over to the chat channel. Tell me if you're good with all this stuff. Everybody just give me a tiny bit of input. Or okay, because then we'll get to the hard part. But I want to make sure everybody's good with this. Okay. Average height. All right, let me go through that again. All right, so on this second rectangle, which here, let me go to a green color here. All right. The height of this point, you can find by looking over here, is 1. The height of this point, we go across, is 5. So the average height, you just average two numbers by adding them together, divide by 2. 1 plus 5 is 3, and so this right here this rectangle, this green rectangle that I'm making right here, has the same area as this other thing over here. It has too much area right here, but that actually fills in the missing part right over here. If you take the average height and the rectangle with the average height, you get exactly the same area. And the same thing over here, if I'd have taken this rectangle. That would have given me the same area as underneath this one, if I use the average height. All right, now...
Can you just use like 7 minus 1 to figure out how high the line is?
7 minus 1. The 7, we don't go all the way over to a height of 7 because we're only going to A6. So I'm not sure what your question is. Can you repeat
I
that?
mean the height. So on the y-axis, the line starts at 1 instead of 0 and the height of 7. So can you minus 7 minus 1 to get the height? And then divide by 2. So it would be half of the height, right? Since it's a triangle, you'd have to do half
Tell
of
me how
base
you got the
times height.
7, the height of 7.
On the y-axis, the line stops at 7.
All right, but we never go out there because we're only going to A sub 6.
Oh, okay, I
When A
see.
is 6 and that occurs down here. We never get out to here. Yeah.
So you just take the line from A of 6,
Uh-huh.
where the line stops on 5, and add 1 to it.
Mm-hmm. Because that's averaging these two values. Add them up, divide by 2.
Okay, that makes sense.
Okay.
Because the middle point of that line would be 3.
That's right. And that gives you the mid height.
Okay, all right, that makes sense.
All right. And now let's go to A of x. There's no way to get A of x without using a piecewise function. You're going to get one formula for it if x is less than or equal to 2, and another formula if x is greater than 2. And when x gets all the way up to 2, this top formula should wind up giving us 4, because we know the area of 2 is 4. So that's kind of a way to check our work. And then we're going to get a different formula for if x is greater than 2. And when we plug in 6 eventually to this bottom formula, we'll be able to check our work. And we better get an output of 16. If we don't, we know we did something wrong. So we got to come up with a formula here for this first one and then a formula for the second one, but we kind of have ways to check our work in both cases. All right. So what I want to do now is, and let me get to erase. Let's get a large eraser. All right. Now let's go with our x. Suppose x is over here and the x is less than or equal to 2. So I put it to the left of 2. If that's the case, then I'm trying to find the area up to here. Now I'm going to use the width, but the width is going to be x minus 0, or just x. And then the height is going to be, well, look at, there's 2 different points. This one has a height of 3. See, I'm going to take the average height. This one, what is the height directly across from here? And for that, I want to ask, does anybody see an insight that lets me figure out what that height is. If the input is x, so we know we're over here on the, maybe a little bit short of 2.
Can you use
A
what do you call it? Like tangent function or something? Make it a right triangle?
We could, but I think there's a simpler way.
Would you just do x plus 1?
It's going to be f of x, so plugging in like your negative t plus 3 there, or your negative.
Yes.
3.
This equation of this line, let me just extend this line out further. The equation of this line is f t equals negative t plus 3. Has a slope of negative 1, y-intercept of 3. So when we plug x into that, we'll get the output. So we'll get negative x plus 3. So for instance, if x was really close to 2, like 1.9, then we would be getting negative 1.9 plus 3, which would be 1.1, which looks like, just like on the graph, a little bit higher than 1. All right, so what we would be getting is right here, negative x plus 3. All right, now we'll simplify that down. 3 plus 3 makes 6 minus x, all divided by 2. Let's simplify this a little further. Take that 1/2 out in front, and then an x, 6 minus x. And then let me go to green. And this, if I distribute this out, this will be 1/2. Well, actually, let me distribute it out. The 1/2 x and 6 are going to make 3x. And the 1/2 x times negative x makes minus 1/2 x squared. So it's going to be 3x minus 1/2 x squared. Now, it's a pretty complicated function because it's a pretty complicated idea. What is the area that I achieve as, as I move this x slowly to the right? But remember, we had said, as soon as we come up with a formula, an idea for it, we need a way to kind of check our work. And we had decided, oh yeah, when you plug in 2, it has to agree with this. And it has to give us an answer of 4. So let's plug in 2. If I plug in 2, I'm going to get 3 times 2, which is 6, minus 1/2 of 4, which is 2. So 6 minus 2 is indeed 4. And that helps me to have confidence in this answer. It works. Okay, now, when x is greater than 2, then I'm going to need something else. So let me go to large eraser, get rid of this stuff. Okay, let's go again. This time my x is going to be like somewhere over here. Now, I know that the area over here is 4. because that was a sub 2. So this area now that's going to go into this portion right here is, we're going to start with, it's going to be at least 4. Then it's going to be more than that depending on the value of x. But we know that x is larger than 2 to use this. So I'm going to do the same thing that I've done. I'm going to do the width. So this rectangle, so now let me make this rectangle in blue. Okay. So to get this, I am going to want the width times the average height. Now, the width of this, if this is x, what's the width of just the blue portion that I drew right over here? Is it still x?
It's x minus 2.
It's x minus 2. And the average height is two things added together divided by 2. But what are those two things? Well, the left one has a height of 1. That's nice. The right one, if the input is x, what is its height? How do I find that? Well, I'm going to do the same thing that I did before. I'm going to plug it into the equation of this line. But what was the equation of this line? Well, let's scroll up a little bit. The equation of this line was f of t is t minus 1. So if the x-coordinate was x, then the y-coordinate, plug it in, it'll be x minus 1. So that's what I'm going to have down here. I'm going to have x minus 1 right here. So now here, this one and this one will cancel each other out. So I'm going to get equal to 4 plus x minus 2 times x divided by 2. And then this will equal 4 plus, now let's distribute the 1/2 x to both parts. So it'll be 1/2 x squared. Distribute the 1/2 x to this, minus, and then the 2's are going to cancel out, and I'm going to get x. So that's what's going to go, and let me put that back in green. It's going to go right here. 4 plus 1/2 x squared minus x, if x greater than 2. Now, we got something really complicated though. So I'm going to be very unsure of my answer until I have some way to kind of check it a little bit. What was the way that we said we were going to check this portion? It was when a is 6. And when a is 6, when x is 6, we're supposed to get 16. So let's put 6 in there. 6 squared is 36. Half of 36 is 18. 18 plus 4 is 22. 22 minus 6 is 16. It totally agrees. That gives me a lot more confidence that I have the right answer. All right, so we have gone approximately an hour, And so what I'd like you to do now is in the text portion of Discord, put in the numbers that you have questions on, the problem numbers. Exclude the ones about the accumulated area, because that's why I did that one practice quiz problem, is to get you ready to do those. But anything else, enter those in now, and we'll take a 15-minute break. So we'll start again at 12:45. All right, welcome back. We'll start again. Just checking over here. Yep. So number 23, the bald eagle population. It says that all right, let me go here. There were that many pairs in 1986, and then there were this many pairs in 2000. Using just the data from 86 to 2000, find a linear function p that models the number of breeding pairs from 86, which will be counted as t equals 0, to year 2000, which will be t equal 14. So what it wants is find a function p of t so that when t equals 0, that's 1986, t equals 14 will be 2000, and in 1986, which is t equals 0, we get 1875, and then when t equals 14, you get 6,471. What it's saying is that you need these 2 points in it. When t equals 0, which is 1986, you're going to have 1,875. That's 1 point. The next point is when t equals 14, you're going to have 6,471 eagle pairs. And now you need to find the equation of the line that passes through those 2 points. And you're going to use, first you find the slope from these 2 points, and then you use y minus y1 equals mx minus x1 to find the equation of the line that passes through those 2 points. And then, once you have the equation of the line that passes through the 2, now actually, instead of y's and x's, you can be using t's. So it could be t minus t1. And for t1, you could use, now this actually has a y-intercept, so the equation might even be easier than this. And then these will be p values, p minus p1 for this. Once you have the equation of the line, then you can answer this question. How much do you expect in 1985? In 1985, I think that's 9 years after 1986. So t will be 9, and you plug in t equals 9 into your equation to figure that out. So that's as far as I'm going to do number 23, giving you a brief overview. Number 25, there was a question on that. And we need a piecewise function. Oops. So we'll put f of x equals, and this is 3, a height of 3. If x is less than or equal to, and it's 3 right there. If x is less than or equal to 3. And then if x is greater than 3, now the equal to sign could have been put here or here, since they both are going to give you the same value. this function right here, we need to find the equation of that line. And I could try to extend the line down and see where does it hit the y-axis. And and if I just kind of guessed at maybe -1, I'd be kind of there. But to be more precise, I might want to say, all right, this point looks like it's the point 3 over 3 up. Where is another place where this intersects at the grid lines? Right here. And you're going to rise 2 and run 1 from that. Rising 2, run 1 is a slope of 2. So this one has a slope of 2 and it goes through the point 3, 3. So y minus y1 equals mx minus x1 is the equation of any such line. We'll plug in 3, 3. We'll plug in the slope of 2. And then we get y minus 3 is 2x minus 6. Add 3 to both sides. Y is equal to 2x minus 3. So that's what's going to go right here. Now, when I had extended this down, I was a little bit inexact. It should have come down a little more and wound up striking it down lower. And so that's going to be then the piecewise function. And then 55. Now, either of these, any questions on 23 or 25? If everybody's okay, I'll keep going.
Can I just a second to copy it?
Number 25?
Yes.
Okay, let me just hold the screen for a moment.
Okay, I'm done.
All right. And then on 55D, question was how to graph that. So I want to make a comment on 55B first. 55B, you have to do this first. Okay, you've got to factor that thing out. Then, this 2 is a horizontal shift, and it's sending you right 2. And then this is horizontal compression. But you'll get the shift wrong unless you factor that out. It's always got to be multiplied by, and then remember I talked to you about horizontal transformations are always replacing the x. It's got to be like when the x is replaced, it's replaced by x minus 2, and then replaced by, so it's got to have that parentheses around it. All right, so on this one over here, D, let me just rewrite the g of x. That 6 is going to be a vertical stretch. It's going to go 6 times as high as normal. And then f of, now I'm going to rewrite it like this. Means the same thing. So we can see that this is vertical this is horizontal. What is this? Is this a horizontal stretch or is it a horizontal compression? When it's a 1, it doesn't do either. It keeps it the same. And it's backwards in the horizontal world. So 1/3 is horizontal stretch. Stretches it out. And then this is sending us to the right. 2. This sends me up 1. So those are all the transformations of y equals, it was y equals x squared for this one. So if I take the graph of y equals x squared, normally that looks, and all you have to do, one of the questions that was asked was, do we have to draw these? Yes, you got to give me quick rough sketches. You don't have to put them to scale. You don't have to label. You just rough sketches. Okay, there's y equals x squared. This new graph, how is it different? It's going to the right. So let me, it goes right 2 units. It goes up 1 unit. So that's the new, right there. That's the new kind of origin. It's going to be going upward. Now, when it's vertical stretch, it goes up a lot faster. Woo, I want to go in. But it's horizontally stretched out. So the horizontal stretching out is, in a large case, going to undo the vertical stretching. And so when you horizontally stretch it out, it makes it wider. When you vertically stretch it, it makes it skinnier. Those kind of fight amongst each other, and you wind up getting something rather similar to a normal parabola shape going upwards, like this. If this had been a 3 instead of a 1/3, then it would be horizontally compressing, which would make it even steeper. So both of these would reinforce each other, and you'd be getting steeper and even more steeper, and you'd have a super skinny parabola. But these were going in opposite directions. They kind of equalized each other out. All right. Any questions there on 55?
I have one.
Mm-hmm.
Do we have to actually like write down shifts like say for like 55A, do we have to say shifts 3 units to the right, or do we not have to do that?
You know, if your scale on your graph, if you have these little markings, and it's pretty clear to me that I can see you went 2 to the right and 1 up, you wouldn't have to label it. But if you didn't have that scale, real nice, then you'd need to show me, you know, say, I went 2 units to the right, and then I went, you know, whatever. Okay?
Okay.
All right. And then, any
Is
other
there an
questions on 55?
Is there an easier way to figure out if the line does a vertical stretch and a horizontal stretch? Like, can you distribute the 6 to figure out how far it stretches or compresses?
Ah, okay. It depends on the function. In this particular function, let's do it. Because it's y equals x squared, so the g of x, there's really a 6. F of anything means to square it. When you square the 1/3, you're going to get 1/9. So it's a very good question, Kylie. And then the 6 over the 9 reduces to 2/3. All right, so the 2/3 is pretty close to 1. That's why this shape is very similar to this shape. But it's as if there was a vertical stretch, a vertical compression, actually. It only goes up 2/3 as fast as this one was going up. So this graph should be a little bit wider, not going up quite as steep as the one on the left, right there. And it all depends on the function. Since this was x squared. If that had been x cubed, then that 1/3 would have been cubed, and it would have had an even bigger effect on this than, you know, certainly it had a bigger effect than the 6 did, because we got a final coefficient of less than 1.
So similarly then, Mr. Shankin, would if it had been 3 times x minus 2, would that have equated to a vertical compression of 54 then?
Yes, because if this had been a 3, if that had been a 3, then when we squared it, we'd have got 9. 9 times 6 is 54, and then the 54 would have been right out in front here. It would have been just like a vertical stretch by a factor of 54. So it would have been super skinny function going way high, really quick. Very good point. All right, let's go to 56. And which one? It was 56B. All right. And 56B, let me just get a big eraser. Well, actually for the notes, I'm going to leave these on. 56B, the one thing I want to point out in 56B is you got to rewrite g of x equals 2f. You got to pull out the 2 here. Okay, so the function has to be rewritten like this to start off with. And then you want to graph the square root of x and then do these transformations. So then, now since the f function is just the square root, this is simply the square root of this. All right, now we can look at what all these things do. This minus 1/2 shifts me to the right 1/2 of a unit. This is a horizontal compression. This is a vertical stretch. Now, if we took all those into account, we would say, hey, the normal graph of the square root of x function looks like this. And how is this going to change? Well, we're going to shift it to the right 1/2 of a unit. So let's make it green. We go, if here's 1, we go 1/2 a unit and we start there. Okay, and then we're going to stretch it vertically by 2, which can make it go higher. But then we're going to compress it, push it in towards the y-axis. Not by quite as much, well, by twice as much as well. So then that's going to make it go up a lot steeper because both actions are reinforcing each other. We're going to get something like this. All right. Now, when you did this, though, we could have also seen that g of x, we could have distributed the square root to the 2 and distributed to the square root to the x minus 1/2. So we could also see that this is the same as just having a vertical stretch of 2 times the square root of 2. And the square root of 2 is about 1.4. So it's a vertical stretch of like about 2.8. And are there any questions here? All right, that's all the ones that I wanted to go over from the homework. Anything else though? Okay, yeah, you gotta sometimes log out and come back in. Sometimes you can just exit the screen share and restart the screen share, and that will help you out.
Mr. Jason? It's Alondra.
Okay,
I was wondering how you got the 1/2 in there. In B.
Yeah, that was my question too.
Okay.
Because I only got one.
All right. So back to here. This part is a problem. You can't have the 2 times just the x, but not times the other factors. So you have to factor out that 2. So it's got to be rewritten as g of x. That 2 out there is fine. But this f of 2 times something. Now, if this had been 2x minus 8, you'd factor out a 2 and go 2 parentheses x minus 4. Now you might say, well, you can't factor out a 2 out of 1. Yes, you can. If it was an 8, it would go down to a 4. It just goes into 1/2 of what it is. When you factor out a 2, you're dividing a 2 out of it. So what you're going to be left with is x minus 1/2. And if you check your work, distribute this 2 to the x, you get 2x. Distribute the 2 to the minus 1/2, you get you minus 1. That's equivalent to that, but it has to be in this format for us to know what the shifts and the stretches are, and so on. Does that answer your question, Alondra?
Yes.
Okay.
Thank you.
You're welcome. Good question. All right. Let's go to the next section. We are skipping 1.3. 1.3 is inverse exponential and log functions. And we are going to eventually do that section. But we'll do it just before we need it, when we have to take derivatives of exponential and logarithmic functions. So instead of doing it now and then giving you lots of time to forget what you learned and then later teach you the derivatives, we're saving that section till when just before we need it. So 1.4, trig functions and their inverses. So we're going to spend some time here now just reviewing the stuff you learned about trigonometry, which is in the last half of the pre-calculus and trig course. All right, and we're going to start with this problem right here. It asks you on this right triangle to find the sine of theta. So let me give you a minute, see if you can recall what in the world was the sine of an angle and how does it relate to this right triangle, and see if you can write an expression for sine of theta. I'll give you a quick minute. All right, let me stop you. So, were you remembering, perhaps you were taught this? SOHCAHTOA in your trigonometry class. And what it's representing is the sine is the opposite over the hypotenuse. Cosine is the adjacent over the hypotenuse. Tangent is the opposite over the adjacent. So the sine of theta is equal to, sine is opposite over the hypotenuse. And from the perspective of this angle here, this is the adjacent side, this is the opposite side. The longest side is never an adjacent or an opposite, it's always called the hypotenuse. It's always opposite the biggest angle, the right angle. And then, so the opposite is x, and the hypotenuse was 6. So the correct answer, the sine of theta, is the ratio of x divided by 6. Now, this will be really instructive for me, so I really need your feedback. Everybody go into the chat portion of Discord and tell me, did you totally forget all the trig, or you, maybe you did but it's coming back, or tell me where you were at with this. I really need to get some feedback here. If everybody give me a little bit of feedback. Okay, we're looking pretty good. Kylie, you said something about taking it a step further to find theta. The only way you can get theta out of inside of a sine function is by taking the inverse sine of both sides.
Oh, that's right.
Yeah, okay. I'm glad you put that in there so we can clarify that. All right, now do B, the cosine. All right, so you have a problem right away with this because the adjacent wasn't given, but actually it is because of the Pythagorean theorem. 6 squared plus x squared, no, 6 squared, equals x squared plus, let's just call this any letter we want. Let's call it w for a second, plus w squared. And then we got to find out what w squared is. So this will be 36 minus x squared is equal to w squared, or w equals, now normally you'd put plus or minus when you square root both sides, but in this case I just want the positive, so 36 minus x squared in parentheses, so that's going to be what w is. So then this is going to be the cosine is adjacent over hypotenuse. And the adjacent was over the hypotenuse, which was this. Okay. Now do tangent. So the tangent is the opposite. SOHCAHTOA, opposite over adjacent. So it's x over the square root of 36 minus x squared, like this. All right, so that's a real brief review of where trigonometric functions came from. It came from right triangles, ratios of, now the two basic trig functions are sine and cosine. Those are by far the most important. And they're a ratio of the adjacent to the hypotenuse versus the opposite to the hypotenuse. And then the other trig functions are kind of, based on those. All right. So we're gonna do this next part, which is to define, and as we do these, I'm going to shift over now, and I'm going to use my camera, and I'm so hang on just a second as I set this up. So we're going to define the cosine and my camera is it working? Let me close it up, try it again. Okay, now it's working. All right, so the cosine of an angle theta. The original definition is if you take a point x, y in space, then as you start at the origin and you move to the right, this distance is x. And as you move up from directly below that point, this distance is y. And as we go out to that point, we'll call this distance r. And then the angle theta will be here, and the cosine of theta by definition is x over r. And the sine of theta by its very definition is y over r. And it doesn't matter where this point is, xy. What matters is that which line it's on. If that xy had been, everything was twice as big, you'd been 2x out and 2y high, the ratios would still all be the same. Or if this was much smaller, what matters is that you stay on the same line. So the angle theta is the same, and it doesn't matter how far out we went on that line. And then the tangent is y over x. All three of those could have been obtained by the SOHCAHTOA acronym, adjacent over hypotenuse, etc. All right. Now, the other trig functions, when you take the reciprocal of cosine, you get, it's called the secant. And it's exactly the same as cosine, but just flipped over, so it's r over x. When you take the reciprocal of sine, you get cosecant. It's the same fraction, but flipped over, reciprocated. All right, now, if you have trouble remembering which one went with which, is the reciprocal of cosine the secant, or is it the cosecant? And if you've had troubles remembering that in the past, there's a really simple memory device that makes it really easy to understand. Notice there's only two starting letters, either C or S. Same thing over here, C or S. And all you have to remember is you can't match the C with the C. The C has to match with the S. The S has to match with the C. They don't match the same letter. So when you take the reciprocal of cosine, you have to start with the other letter, S. Take the reciprocal of sine, you have to start with the other letter, C. And then there is the tangent. Its reciprocal is cotangent, is x over y. And the next problem I want you to look at is convert 20 degrees to radians. And let me give everybody a minute to do that. Okay, so it may have been a while since you've done these conversions. And if you thought that you had to memorize this ratio of something you had to multiply it by, that's not correct. You don't have to remember something to do this. You have to really just understand something. So let me point out what I mean. If I told you to convert 3 feet to inches, you do it in this way. 3 feet, and we all know 3 feet is going to be 36 inches, but this is the process that makes it, gives you something to translate over to here. Remember this. I want feet to go away. So, and what I want it to be replaced by is inches. And then I take equivalent units. I take 1 of the bigger one and 12 of the smaller one. It's not always 1, but just something that they're equivalent amounts over here. And then what's going to happen is the feet cancel out, and I'm going to get 36 inches. So we're going to do the same kind of thing here. 20 degrees times, I want degrees to go away, I want radians to show up. I need something equivalent. I can either go entirely around the circle, that's 360 degrees, or halfway around will be good enough. 180 degrees is the same as pi radians, as long as these are equivalent. I could have gone 360 and 2 pi. It would have turned out to be the same. And then we reduce this. Now the zeros cancel out, and 2 over 18 is the same as 1 over 9, so it just becomes pi over 9 radians. And the radian is one of those units. It's a crazy unit in this way. It's really a unitless number. So it's optional to write down the units of radians. And thus when it's not optional if you're in degrees. You have to write the degree symbol. But radians, we often see it without it. And we'll see throughout the textbook as we go on that in calculus we'll very rarely deal with degrees. Most of the time with radians, and they often won't even tell you the units are radians. A little feedback again would be really good here. How many of you remembered and were able to do this? And then you, even if you were not able, you can just say, yeah, but I wasn't able to do it, but I'm good now. Or just give me a little bit of feedback here. If everybody can give me a tiny bit. Okay. And let's come back to the camera. And the basic shapes we're going to need to remember this stuff for these curves. Y equals sine of x. Go ahead, give me a quick picture. Draw y equals sine of x. And then y equals cosine of x. Draw me a quick picture of that. Okay, I'll give you 30 seconds more. Hopefully it's something you remember real quick. Alright, for both of these, the period is 2 pi. Now, pi is 3.14. And so about 1/3 of that should be my height. which is 1 and negative 1, and then 2 pi. Okay, the sine function starts at the mid-height, and every quarter of the way it changes. It goes up to its highest, back to here, down to its lowest, back to here, and we complete it with a smooth curve, like this. And the cosine, I erased that. It starts at the highest. Every quarter it changes. Get this smooth curve. Like this. Alright. Now, I'm going to erase some stuff, but before I erase, what I'm going to do is I'm going to do a print screen. I'm going to go into OneNote, and I'm going to paste. Oh, come on. Let's do this again. Oh, no, oh, I know. We go to here. Control, print screen. Let's try this again. No. Hang on a second. Let me get technical support help.
Are you using Windows?
Yeah, Windows.
So press the window button and then print screen.
To do a print screen?
Yeah, press the window button and then the print screen. And that'll take a screenshot of their
I thought it
whatever
was
your camera.
control print screen.
Yeah, I looked it up and it says
It's
that you have to press
the
the
window
Windows
button.
key.
You can also use this, what is it, the Snip and Sketch app.
For that
So
too.
that can,
Okay.
yeah, but that gives you the option to do like portions of your screen instead of just your entire screen.
Again.
You can do Shift Windows S, and that takes a snip that you can change the size of.
Aha. There it does. Okay. So I got that into the notes. And all right. And then let's go with all right. Come back to the camera. And I'll erase. And let's do a non-basic shape. Suppose we were told to graph y equals negative 2 sine of 2 parentheses x minus pi plus 1. Alright. To graph all of this, we would use exactly the same strategy that we were just using in our transformation section. So this 1, what effect? This takes this basic graph of the sine of x and makes it go up 1. This one, notice the 2 is factored out, had to be factored out. It couldn't be, the 2 inside the parentheses with the x, had to be out there. Then this is going to send me to the right pi. Now you put these two facts together, I'm going to call it a new origin. Pi units up or pi units to the right, 1 up. So when I graph this one, I'm going to go pi units to the right and up 1, and that's going to be my new origin. Now notice the effect of the origin on here. We started at the origin and went on up and around. Now, from here, let's look at what else happens. This, what do we call a number right here? We call it a horizontal, what, compression or a stretch? It would be a horizontal compression by a factor of 2. Now, that's normally called horizontal compression factor of 2. But we learned in Trig this thing called how it affects the period. New period is the old period divided by that number. Now the old period, the normal period of sine is 2 pi. Now, instead of a period of 2 pi, we only have a period of pi. That's the same as horizontal compression by a factor of 2. We squished it in horizontally, so it only takes up half the amount of space before you're done with one period. Okay? And then, what did we do with this one? This 2 right here, we had a fancy name, we called it the amplitude. But the amplitude is from the origin how much you go up and how much you go down. So we're going to make a little box here. We're going to go up 2 units and down 2 units. And then we're going to go over 1 period. And I'm going to make this box. So the entire graph will fit inside this box. And then I'm going to draw my curve. Now here's my midline right here. And my sine curve starts here at the 1/4 point. It goes, normally it would go up, but this is reflection across the x-axis, so everything is reversed. So it's going to go down, up, up, down, and we get this shape right here. And so all the stuff we learned about graphing trig functions in trigonometry is really just another application of transformations. And we only have a short amount of time left. Let me put a quick put this into the OneNotes as well. Okay. And the last thing I want to do is having to do with inverse trig functions. To refresh that quickly for you. The inverse cosine of 1/2. It asks this question. What is the angle whose cosine is 1/2. Now, am I writing too small for you? Anybody having that problem? Okay. So we can visualize this, and we think of the unit circle. What's the angle that when I take its cosine, I get 1/2? Now the cosine on a unit circle, if this is length 1, on the unit circle, the cosine corresponds to the x-coordinate. So I just go to 1/2 right over here. What is the angle whose cosine is 1/2? It's going to wind up being up here. This angle. And how do I get 1/2? Another way to look at this again, inverse cosine. Let's just call this a value for a minute. Let's call it, since it's an angle, let's use a Greek letter. Then let's take the cosine of both sides. So then cosine of theta, what happens to a function and its inverse? Kill each other off. This is also asking, what is the angle who, when I take its cosine, I get 1/2? But it's stating it in a forward sense rather than in an inverse trig function sense. All right? And so on here, again, on this, we could give, on a unit circle, we could identify all the points on the exterior of a unit circle. This is 1/0 up. This point here is 0/1 up. And if I had a 45-degree angle, that would be square root of 2/2 over, square root of 2/2 up. If I had a 30-degree angle, which is the same as pi/6, it would be the larger number over, square root of 3/2 over, the smaller number up, 1/2. If I'm over here, I go the smaller amount over, the larger amount up. And what is this angle? It's right up here. Theta turns out to be pi/3. We will be using radian measure rather than calling it 60 degrees. And this takes us to the end of our time. The homework is 1.4, and in 1.4, numbers 86 and 94, I want you to check with your group members. Make sure that you're correct on those two. And before we leave, any questions, comments? All right, we'll stop here for the day. Oh, and I have to stop.
Professor Shankin,
Yes.
this is Neil Crozier.
Hey, Neil.
I don't know if you noticed that I'm been most of the class. I got in a little bit late because of my other conflict.
Great.
But I bailed out of there as soon as I did my little presentation.